Welcome back. Last video we have seen certain properties of Fourier transform of a periodic signal, and we will have one more property that is just the equality you can derive if you are given a two such functions, two time signals. If you are given, we will just write that is called Parseval inequality. So, property number 7 which is Parseval's inequality, Parseval's equality identity. So, that is L by 2 to L by 2 f x g x bar dx is equal to n is from minus infinity to infinity. This you can get f cap of n into g cap of n bar. So, this is Parseval's identity. So, you will know its importance when we do the Fourier transform on non-periodic function, that is a function defined a signal over a full real line. So, what we do, so here we do, so what is the cap denotes the Fourier transform of a periodic signal. Both f and g are piecewise smooth functions. So, to prove this we consider h of x be f x into g x. So, we already know if we are given a product of functions, what is its Fourier transform. So, h cap of n is actually equal to, you get this as a summation from minus infinity to infinity f cap of k into g cap of n minus k. We have seen as a property number earlier, property number 4, I think 4, right. So, property number 5 that you have seen this equality. Once you look at the, once you have the product of two functions, which Fourier transform is given as convolution product of these sequences f and f cap and g cap. Now, if what I do is here I choose n equal to 0. So, so h cap of 0 will be equal to k is from minus infinity to infinity f cap of k. So, once you choose this n equal to 0, and you have g cap of minus k. So, what I choose is if I choose g of x, if I take it as g of x bar, if I replace, okay. If I replace this with the g with g of x bar, what happens to g cap of n? This is integral 1 by L minus L by 2 to L by 2 g of x into e power minus I n omega naught x dx. So, this is equal to 1 by L, gx is gx bar, if you put it e power minus I n omega naught x dx minus L by 2 to L by 2. So, this is what happens. So, now if you take the bar, two bars, then one more bar if you take two bars. So, if you apply the lower bar here, so this goes and this is going to be plus. Okay. So, this is bar of g cap of minus n. So, what you get is g cap of n, this is true for every n if g of x is gx bar. Okay. So, I choose, so you have the in your Parseval identity, what you have is this relation, this integral f x into gx bar dx, this is equal to so that is exactly your h dash of 0. So, what is h dash of 0? H dash of h cap of 0, h cap of 0 is exactly 1 by L integral minus L by 2 to L by 2 by definition. This cap is h of 0 is h of x into, that is f x g x e power I n omega naught x is 0. So, n is 0, that is going to be 1. So, dx. So, this is exactly our h cap of 0. So, this one is exactly equal to this from this relation you can say that minus infinity infinity f cap of k g cap of minus k bar, okay, because of this. If I replace g by g dash here, so what you get is and from this you can easily see that this is this. So, this is going to be plus, right, g cap of minus k. If I replace g by g bar, and you have what you have to replace is g bar of g cap of n is bar of g cap of minus n. So, I have a bar g cap of, I have already minus k. So, it is going to be minus of minus k, that is going to be plus k. So, this is exactly the equality we derive. Okay. So, this is the Parseval's inequality. So, if f of x equal to g of x, if I choose both are same, and what you get is 1 by L integral minus L by 2 to L by 2 modulus of f of x square dx. This is equal to k is from minus infinity to infinity. This is going to be f cap of k square. So, this is called Parseval's identity. This is also you can, so this is the implication if you choose g as or f as g of x or g as f. If you simply consider g of x equal to f of x in the above identity, then what we get is this identity. So, this is one important property whose importance you will see eventually when you do the Fourier transform. So, we will just have a recap of what we have done. Before I do this, I will just explain. We have defined what is a delta function. Delta function is basically you consider all these functions, you define minus L by 2 to L by 2, some step function like this, so that whose area is 1. So, that is your f1 of x is 1 between minus L by 2 to L by 2, 0 otherwise. So, you define it like this, that is your f1, so that whose area of f of x dx is over minus infinity infinity is equal to 1. So, that makes this height is simply L. So, and so on. So, you go on doing like this. Next time you do it from half of the distance minus L by 4 to minus plus L by 4 plus L by 4. If you define the same way, so what you do is you have to increase your height, that is your f of 2 of x, that is going to be again 1 not 1. So, some quantity a, so that so when it is, what is that quantity? If you choose this as L, then this is going to be 1 first for f1. Similarly, here I have to choose L by 2 between minus L by 2 to L by 4 to L by 4, right, otherwise 0. If I choose like this, right. So, this is integral of this is L by 2. So, this is 1 by L. So, this is going to be 1 by L, and this is going to be 2 by L and so on. So, whose height is 2 by L, whose height is 1 by L and so on. Okay. This is height is L by 1 by L, this height is 2 by L. So, you can go on doing like this, finally you can get some sequence of usual functions f n x as n goes to infinity. So, as n goes to infinity, what you see is this length of this interval is coming smaller and smaller. It is going to be, what you see is exactly infinity, that is not is going to infinity, as L goes to 0 is going to be infinity, as n goes to infinity L is going to 0, as L goes to 0, this height of this function every time is depending on 1 by L is going to be infinity. So, that is at x equal to 0, 0 everywhere else. So, this is your delta function, that is how you defined it. And if I choose, if I need only and then, so one of the property of the delta function is minus infinity infinity delta x dx is equal to this is simply delta x acting on, so this is into 1 dx. Okay. So, delta x dx is actually equal to 1, or simply if you multiply delta x to f x, this is going to be this is also we have seen in the earlier video that we can easily show that this is actually equal to f of 0. Simply allow this definition of delta function limit of f n's here, and you can easily see that is going to be f of 0. Now, what we need is if I have 0 to infinity instead of minus infinity infinity, if I have a 0 to infinity, I have delta x f x dx. What is the value of this? This is actually equal to half of f of 0. Okay. So, that is the result we want to show. So, how do I show this? Just apply. So, the LHS is you have LHS equal to, you can allow this limit f n of x f x dx as n goes to infinity. So, assume that you can do this limits outside, limit n goes to infinity 0 to infinity f n of x f x dx. Okay. So, if f is piecewise continuous functions, smooth functions, these are converging things. So, you can uniform convergence will allow you to take this limit outside. So, that is not difficult to justify. So, you have this limit outside. Now, you can evaluate this, these are the usual functions, this limit n goes to infinity. What you have is it is going to be 0 to L by 2, f n of x is, if you have one is f 2 is 2 by L. So, this is like n by L, right. So, you have n by L between 0 to L by 2, otherwise outside it is 0 into f x dx. Okay. So, this is equal to so again, so you have this limit, the same idea that we have used. This is the integrable function. So, n by L times. So, integral 0 to L by 2 f x dx, that is L by 2. So, this minus this b minus a, if I use the fundamental theorem of integral calculus, b minus a into f of c, where c is between 0 to L by 2. So, this is L goes limit n goes to infinity. So, 1 by 2 comes out, and this n into f of c. Sorry, there is a mistake. So, you see that f 2 is 2 by L, but the length is every time is minus L by 2 square. So, you have minus L by 0 to minus, because this interval is fn of function is defined over minus L by 2 power n to L by 2 power n. So, that is what you have. So, you have this is from 2 power n. So, L by 2 power n, L by LL goes 2 power n. So, 2 power n into f of c. So, you have n divided by 2 power n f of c. Now, as L goes to 0, this is c is going to 0. So, what you get is, and n divided by 2 power n is going to be 1, the limit is 1, power n is n power, then do this n power n. So, L by 2 power n minus 0 into f of c, c is this, LL goes, and what you get is so we have to define, I think we should have minus L by 2 to L by 2, that is your f1 of x. f1 of x is defined as 1 by L if it is minus L by 2 to L by 2, otherwise 0. f2 of x is 2 by L between minus L by 4 to L by 4, so 0 otherwise. So you have fn of x is n by L, it is if x belongs to minus L by 2 power n to L by 2 power n. L by 2 power n, so L by 2 power n minus 1. So what you get is, this is not 2 by n, so this is not n by L, it is going to be L by 2 power n minus plus L by 2 power n, whose area is that it is going to be A into this, so this is L by 2 power n minus 1 is equal to 1. So A equal to 2 power n minus 1 by L, right, 2 by n power. So if you want that area of fn of x dx equal to 1, that is between minus L by 2 power n to L by 2 power n, if you want this, and what you get is, if you make it as a constant, so you have a should be equal to 1, so area should be 1. So what is this area is L by 2 power n minus 1 into A equal to 1. So this makes it A as 2 power n minus 1 by L. So you have 2 power n minus 1 by L, otherwise 0. So this is what is your fn of x. So not exactly n by L, it is actually 2 power n minus 1 by L. So here instead of what you have, now you can get this 2 power n minus 1 divided by L times this difference L by 2 power n minus 0, that is this, into f of c. As L goes to 0, c goes to 0. So this is going to be so 2n goes, finally if 2n goes, 1 by 2 is there, what you get is L goes, and you have 1 by 2 comes out, you have simply this. That is going to be, as n goes to infinity, L goes to 0, as n goes to infinity, L goes to 0, as L goes to 0, c goes to 0. So this is going to be f of 0, because f is smooth function. So such a thing, so f is piecewise continuous. If you take, this is what is the result. So if you can see that if you multiply delta function to a function, to a suitable function fx, what you end up is piecewise continuous function. If you take, so what you see is this result, half of actual value f of 0. So if you take the full thing, if you take minus infinity delta function, you have f of 0, otherwise only half contribution will be there at the pole at 0, at x equal to 0. Okay. So that is what is, it will be useful when you do the Fourier transform later on. With this we will have a recap of what we have done for Fourier series. Fourier series, so far what we have done is, if you consider a signal that most probably you can have a piecewise, that means you have finitely many discontinuities, and those discontinuities are jump discontinuities, and it is a continuous function. It is a continuous function, piecewise differentiable function. Piecewise smooth function means it is many times it is piecewise differentiable function. N derivatives, if we consider n derivatives, if fn is any n derivatives of the function fn, any nth derivative of the function of the signal, that is fn, nth derivative of function is piecewise piecewise continuous function, piecewise differentiable function, piecewise differentiable function. When we say something is piecewise differentiable function, you simply consider its derivative which is piecewise differentiable, piecewise continuous function. If it is piecewise continuous function of first derivative, you say that it is piecewise differentiable function. Any nth derivatives you consider which is piecewise for every n, you say that it is piecewise smooth function. Okay, that smooth means you have all derivatives, many derivatives exist, every derivative you take it is a piecewise continuous function, then you say that it is a piecewise smooth function. So, when you have a piecewise smooth function, what you get is you have a Fourier series. You can define the Fourier coefficients, and you composed all of them as Fourier series, and this Fourier series is, you have shown that it is uniformly convergent. Fourier series itself is uniformly convergent and absolutely convergent series, so that you can do some manipulation with the series. You can differentiate term by term, you can integrate term by term because of the uniform convergence of the Fourier series. Okay. For that we have used many results that we have used only a few results that are required here. To start with, to show the convergence of the Fourier series when you have a piecewise differentiable function, what you had is Bessel's inequality and Riemann-Lebesgue lemma. What happens to the Fourier coefficient as n goes to infinity, that is the Riemann-Lebesgue lemma. Using them, if you have a piecewise differentiable function and you have seen that Fourier series actually converges to the function value, pointwise convergence you have seen. The Fourier series actually converges, if you fix x value, a Fourier series of the function f x converges to the function value f x if f is continuous at x. Otherwise, both sides limits at x, suppose it is not continuous, it should be, it is discontinuous at that point x, but there are jump discontinuities are only allowed, because that is how we restricted our signals are, and both sides limit exists. If it is jump means both sides f x plus and f x minus, both sides limits exist, and we take the average of them. So, the average jump, half of the jump is exactly where this Fourier series converges to the value. If it is piecewise smooth function, we have actually seen that this Fourier series is converging uniformly, implies by the corollary of Bessel's inequality, you can see because the signal by the Bessel inequality, sigma Cn square, sigma we have seen that sigma series, absolute series of Cn's, this is finite. You have seen this is the result when it is piecewise smooth. Once you have this, that means this once you see that this is true, implies Fourier series is uniformly convergence. That means Fourier series is actually converging even pointwise. Once it is uniform convergence, it is also converging pointwise. That means, so you have a Fourier series composed of Fourier coefficients and signals, fundamental signals in terms of exponentials e power I n omega naught t. So, in terms of them, Fourier series that converges pointwise. Once you know this is true, and it has to, where it has to converge, that we do not know, if f is piecewise, just piecewise continuous function. Okay. We know that if it is piecewise smooth, this is always true. Okay. Implies Fourier series actually convergent, that is trivial. We have seen that if it is a differentiable function, piecewise differentiability implies Fourier series converges to the function value pointwise. But if it is piecewise convergent, we know that this series is finite. So, that means it is uniform convergence, implies that then the Fourier series converges to the function, that is also trivial. So, only thing is when, so if you assume this, that means if f is piecewise only continuous function, piecewise continuous function only, then you do not know whether this is true or not. Okay. This result is true, you have to include piecewise smooth function. Okay. That means at least two derivatives of the function f x, f double dash of x is piecewise continuous function. Then we have shown that this is actually true. That implies uniform convergence. That implies you can whatever you can actually show that the Fourier series converges to f(x) in the second result. So, we use the crucial assumption that this is true if this is finite. If this is finite and if it is piecewise continuous function, okay, f is a piecewise continuous function, piecewise only continuous function. If these assumptions both are true, then the Fourier series converges to f(x) or the average value of x, whether it is a discontinuous or continuity, depends on that, it converges to the function. Okay. But we do not know this result. If it is piecewise continuous function, you cannot guarantee that this is true. Okay. Convergence of uniform convergence of the Fourier series, it is not guaranteed, or in fact convergence. Okay. So, this shows the convergence. If this is actually true, implies uniform convergence, that is what we have seen in the last video. So, but in general, for when you have a signal which is piecewise differentiable, piecewise continuous, obviously its derivatives also exist that are also piecewise. You basically if you represent your signal with elementary functions, they are actually composed of what you see is if you calculate the derivative, they are not differentiable at most at finitely many places, wherever they are not differentiable. Okay. If it is piecewise continuous, at those certain points you have finitely many points at which it is not continuous, at those points it is not even differentiable. So, within the gaps you have a piecewise differentiability, that means a derivative is piecewise differentiability, that means it is you take any signal you represent by elementary functions, your signal is always piecewise smooth, implies Fourier series actually converging uniformly, okay, and absolutely, implies your convergence theorem, Fourier series actually converges to the function f or its average value depending on its continuity at the point x or not. Okay. So, that is what we have seen, and later on using the Fourier coefficient Cn, that is 2 by L integral minus L by 2 to L by 2 f(x), this is how we define Cn, we call this f cap of n. This is the definition of the Fourier transform I n omega naught x dx. Okay. So, this you have seen minus with minus, this is your definition of a Fourier transform. Once you your Fourier coefficients, if you represent as a transform, what your Fourier series is actually your inverse transform, and you have seen certain properties on these Fourier transforms that include linearity, scaling, time scaling and other things. Okay. And you have defined product of what is a Fourier transform of the product of the function, and what is a Fourier transform of its convolution product, what is a Fourier transform of its convolution product, and you have also seen today Parseval's identity. Okay. These are the important properties through which you can actually calculate, if you are given a complicated function as your time signal, you make use of these properties and evaluate the Fourier series. Okay. That is the importance of these properties as of now. So, this is what we have done in the process. We have also introduced what is a delta function, which is not a function, which is simply as a limit of usual functions f(n) of x. Usual means what we do not know, it can be some sequence of functions f(n). If you take the limit which is not a function, if delta x is not a usual function, limit of usual functions, if you view this as a limit of usual functions, then you call this generalized function. Okay. Generalized function. So, delta function is one such function. So, delta function is a generalized function, and whose properties you have seen. So, how you get this delta function, as you have seen how to construct these fn's, so that it converges to it is amounts to what is limit of that is delta function. And one of the property of the delta function is, if you multiply delta function with another function and integrate, its value that value is actually functional value at 0. Okay. And if you take only integration from half of that from this singularity, so from 0 to infinity, if you take delta is basically delta of x means it is at 0 you have a singularity, so delta x, delta 0 x, because at x equal to 0 this is infinity. Okay. So, if you integrate only from 0 to infinity, half of that, so the singularity for the singular point infinity at which the function is delta function is infinity at 0, if you integrate half of that singular point contribution will be there, that is going to be half if you integrate from 0 to infinity, or minus infinity to 0, both sides because of symmetry what you get is this delta x dx will be only half. Okay. This is the result we have seen today. So, with this we close the Fourier series part. So far you have seen a signal function f(x) as periodic, piecewise continuous or piecewise differentiable function, okay, piecewise smooth function if you represent as elementary functions. But see, if your function f of x, if your signal is f of x is a even function, what we have seen is you can see that the Fourier series is f of x is, assume that if it is even. So, what is the even function? F of x equal to f of minus x for every x, that is the meaning of even function. So, if your f of x is defined between minus L by 2 to L by 2, and you have this is always true, minus L by 2 to L by 2, wherever it is defined, this is periodic function which is even function. And what is your Fourier series representation? F of x is, you have a sigma, n is from minus infinity to infinity, you have f cap of n, Fourier transforms e power I n omega naught x, omega naught, yeah, this is your Fourier representation for every x in minus L by 2 to L by 2, okay. And you have f x if x is continuous, or if it is x at x, if it is not continuous, you simply take f x plus f x minus half of that, average of that, that is what is the representation. This is your Fourier series. And what happens? So, you have if f is even, what happens? Fourier, you can start with the Fourier series, n is from minus infinity to infinity, f cap of n into e power I n omega naught x, which is equal to, I simply split into two parts, okay. So, n is from minus infinity to 0, f cap of n e power minus I n omega naught x, plus n is from 1 to infinity, f cap of n e power minus I n, this is not minus, this is plus, okay, I n omega naught x. So, this is equal to f cap of 0 plus, and this you try to replace n by minus n, then it is going to be 0 to infinity, there is going to be 1 to infinity, f cap of minus n e power minus I n omega naught x, okay, plus sigma n is from 1 to infinity, f cap of n e power I n omega naught x. So, what is your f cap of n? Is 1 by L minus L by 2 to L by 2 f x e power minus I n omega naught x dx. Because f is even, you make use of the idea, property that f is even, and this is because it is even, you have 2 by L times, this is going to be 0 to L by 2, f x is even, right, and this function is, so if you use this f x e power minus I n omega naught x dx plus 2 by L minus L by 2 to 0 f x e power minus I n omega naught x dx. So, what is this one? First part as it is, f x e power minus I n omega naught x dx. The second one, you replace x by minus x, then what you get is 2 by L, this is going to be L by 2, if you replace x by minus x, this is going to be L by 2 to 0, and f of minus x, and which is f of minus x is f of x, because f is even, and e power I n omega naught x, dx is minus dx. So, that minus part you can write 0 to L by 2, okay. So, this is what you have. So, this is nothing but 2 by L, where do you get 2 by L? is not 2 by L, it is 1 by L. So, 1 by L is only continuing. I split it into 2 parts. So, what you get is, now this is going to be, if you add it together. So, you get 2 by L 0 to L by 2 f x, and this you add up. So, you get cos n omega naught x dx. So, your Fourier coefficients are only this, okay. So, are only this, and now you can easily see that f cap of minus n, from this f cap of minus n is also f cap of n. This is true for every n. Now, if you use this here, so these are f cap of minus n, I can replace with f cap of n, okay, and that makes it, I can remove this part, and this is what you get. So, e power I n omega naught x, okay, the summation. So, this summation is nothing but you have 2 times cos n omega naught x is my f x or f x plus f x minus divided by 2. So, this function, this is your Fourier series and this is your Fourier coefficient, okay. So, this is your Fourier coefficient, and this is your Fourier series. If f is even function. So, this is also called Fourier cosine transform, and this is your Fourier cosine series. What is your f cap of 0? F cap of 0 is simply 2 by L integral 0 to L by 2 f x dx, that is your single constant, okay. F cap of 0, and with this f cap of n, that is only running from 1 to infinity, you have, instead of exponential functions, now what you have is cosine functions. So, this is what happens if it is a even function. If you a priori, if you know that your signal is symmetric with x equal to 0. So, minus L by 2 to 0 is symmetric to 0 to L by 2. So, if it is symmetric both sides, something like a signal will be, so if you take the hat function, this is symmetric both sides, okay, symmetric at about x equal to 0, it is a even function. If your function is like this, if it is like this, which is here is the positive, here is negative. So, this is odd function, okay. For example, you can have a sin x function, sin x, how does this look? Sin x function between minus pi to plus pi 0, this is how it looks. So, you see that minus pi by 2 is the negative of that. So, this is the odd function. If you take cos x, but if you take cos x, cos pi is minus 1, cos minus pi is minus 1, cos pi is 0, cos pi by 2 0. So, this is how it looks. So, this is even function. So, depending on even function or odd function, you can work with this Fourier series, and in the odd case, if f is odd function, if f of x is odd, that means f of x is minus f of minus x, or you can write f of minus x is f of minus of f of x for every x in minus L by 2 to L by 2. Such a periodic function if you have, what you get is f cap of n, the Fourier transform will be in this case 2 by n between 0 to L by 2 f x. Instead of cosines, now you get sine n omega naught x dx, you can easily see, and your Fourier transform will be n is from 1 to infinity, because it is even function f cap odd function f cap of 0, that is integral from minus L by 2 to L by 2 f of x dx, that is going to be 0 because f is odd, right. So, you have a minus L by 2 to L by 2 f of x dx. If f is odd function, you can easily see that this is L by 2 f x dx plus minus L by 2 to 0 f x dx. Now, if you put x by minus x, you have a minus f x, that is going to be L by 2 to 0, and dx is minus dx. So, you can revert these limits. So, this is what you get. So, finally, it is 0. So, because of that, this cap in the Fourier series, this f cap of 0 will be 0, otherwise the Fourier series will be 2 times f cap of n is from 1 to infinity. Instead of cosines you have now sines, sin n omega naught x. Okay. So, this is exactly equal to f x, odd function f x, if x is continuous, or if it is not continuous, you have to take the average value of it at average value of the jump, depending on if f is continuous at x or not. So, this is our Fourier series, Fourier sine series, and this is Fourier sine transform. So, if it is odd and even function, this is the case, and sometimes you may have a signal only on the positive side, 0 to only half of that, if you are given 0 to L by 2 only, you have a signal. So, left side you do not know really, but you want to have Fourier series of period minus period L. If you want to have a Fourier series of length with period L, you can extend your signal here as either as a even function or odd function. Suppose this is f of x, how do you extend this function over x belongs to only between 0 to L by 2? You can extend this function as itself if x belongs to 0 to L by 2, and f of minus x if x belongs to minus L by 2 to 0. So, if you put x equal to minus L by 2 to 0, is going to be values here only. So, this is the even function, even extension. This is useful in even and period, this technique we use. You can also, this is like even, we can write f even, and you can also extend it as f odd function, and then how do you do this? F x, x belongs to 0 to L by 2. How do we get the extension for the left hand side? Minus of f of minus x, that is going to be if x belongs to minus L by 2 to 0. So, this is odd extension. So, once you have this, if you have a signal only between 0 to L by 2, you can extend it to a length of a period of up to L with the period L. You can extend as even or odd function, and you can give the Fourier series in terms of cosines or sines, depending on how you extend the function over the full period L. So, that you can get the Fourier series with period L. Okay. So, using these Fourier sine transform and Fourier sine series, or Fourier cosine transform and or Fourier cosine series. Okay. So, this way you can have, so we will try to give you some problems on these whatever we have done on the Fourier series, and problems will be given as an exercise, you can work out. So, in some of the problems you may have to use properties that I have explained in the last videos. With this we end this Fourier series part. In the next video we will start Fourier transform, that is you can consider a signal that is non-periodic, that means something is non-periodic means you have a signal that is defined over a full real line. So, there is not like a finite part over which it is repeated outside. So, it is extended fully. If you have a non-periodic function, how can you get a Fourier transform and its inverse transform? That is what we will see. So, we will see these things as we will define what is Fourier transform and its inverse transform in the next video. Thank you very much.